All right, let's use Green's theorem to compute an example. In this example, we're asked to compute the path integral f dot dr, where f is given to us by this formula, and the arc, so the c, the curve, consists of the arc of a cosine curve, y equals cosine, between 2 points, and then the line segment that connects the rest of it. So let's start by sketching the region here. So I say the region because I'm already thinking about Green's theorem. So this one says, here's our point, pi over 2, comma 0. Here's our symmetric point, negative pi over 2 comma 0 over here. And our curve goes from this point to this point, follows a cosine arc, right? So this is y equals cosine of x. But we're told that our curve is oriented this way. And then it's closed off, so that's like C1, you would say. It's closed off by this curve. So this is C2. That's just a horizontal line segment. And call this C1. And we're asked to find the work of this vector field along this closed path. Now, it's probably possible to compute this, although we see some exponentials. We're going to have to parameterize in terms of cosine, maybe x, and things are going to be going around here. We have to then treat this curve as two different segments, right? And so this one is kind of screaming to us to at least try to recognize this integral instead of being a path integral, but recognize it as an area integral, where the area is enclosed by this path, and the path does have positive orientation, right? And so let's try to use Green's theorem. Remember, Green's theorem says that the path integral f dot dr is equal to the double integral, so the area integral, of dq dx minus dp dy with respect to area over the entire region. And so at this point, we want to ask ourselves if this is even better, right? So what happens if we take dq dx minus dp dy? Okay, so let's find out. So dq dx, remember the p and the q are the components, right? So there's q, here's p. So in Green's theorem, the function that we create is dq dx. Well, dq dx is not gonna have any exponentials. It's just going to be 2x, right? So just 2x, and dp dy is going to be similar. So dp dy is going to be, again, exponentials not involved, it's just going to be 2y. And so then the function that we want to integrate is the difference of these two. And so our dq dx minus dp dy function is just going to be 2 times x minus y. Okay? Not bad. That looks like something that we will be able to integrate. The next thing we need to do is be able to make sense of our region, right? And so our region is bounded by cosine. It's also bounded by the x-axis, so we can treat this like a type 1 region, where we integrate out the y direction first, the cosines first, and then go from left to right and integrate the line segment up. So that means then that our boundaries for y are just going to be from 0 up to cosine of x, and our boundaries for x, once we've done that, is just negative pi over 2 to positive pi over 2. And so this integral, area integral shouldn't be too bad. So let's check it out. What we end up with then, by Green's theorem, right, is the integral f dot dr is equal to the iterated integral from negative pi over 2 to pi over 2 of the inner integral 0 to cosine of x. Integrand is 2x minus y, and we've decided to integrate this as type 1, so it's dy dx. Okay, and we just compute this now like an iterated integral, and then we're done. So let's just do this quickly. We end up with negative pi over 2. Pi over 2, this inner integrand, the 2's hanging out, right? We integrate with respect to y. We get xy minus 1/2 y squared. And we're plugging in y equals 0 to cosine of x. When y is 0, it zeroes everything out, so that's nice. And when y is cosine, we're left with some work to do. So integrand is now going to be 2x cosine x minus 1 cosine squared x dx. Okay, and we just have to integrate these two. So this one's an integration by parts. This one is a trig substitution. So I'll just do these separately over here. If we have, I'll color code it though. So we'll call this our integrand I1, And on this one, including the minus, our integrand I2. So for I1, what do we have? This has got to be done by parts. So our u is 2x, and our dv is cosine x. Integral of cosine x is positive sine of x. And so, what do we end up with here? Just by doing our little plus, minus on the table, we end up with, this should be 2x sine of x plus 2 cosine of x, and we plug in our boundaries. So x goes from negative pi over 2 to positive pi over 2. All right, and then this I2 integral. So the I2 integral, cosine squared x, negative cosine squared x, is equal to negative 1/2. 1 plus cosine of 2x. And so when we integrate that up, what do we get? So we can just distribute this, right? Negative 1/2 minus 1/2 cosine of 2x. And so this gives us minus 1/2 x minus, this is going to be 1/4 sine of 2x. And so all of this, also we plug in x equals negative pi over 2 to pi over 2. This is not the most riveting stuff for a video, but you got to be able to compute all this, right? So sine of pi over 2 is 1, sine of negative pi over 2 is negative 1, cosine of pi over 2 and negative pi over 2 is 0 for both of those. So this is just going to give us 2 times pi over 2 times 1 minus 2 times negative pi over 2 times negative 1. All right, plus, so sine of negative pi over 2 is negative 1, right? Just make sure I've done all this right. And then over here we have, this is going to be negative 1/2 of pi over 2 plus pi over 2. So that'll give us something non-zero. Minus, and then here again we have 1/4. This is going to be what? Sine of pi is 0 though. Same as sine of negative pi. So, a lot of stuff canceling out here. This is just pi. This is going to be minus pi. So this whole thing, as long as I did this right, this is pi minus 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 pi. So that's 0. This one's obviously 0. And what we're left with then is negative. This is just pi, right? This adds up to pi. So negative pi over 2. And so this is equal to, of course, by Green's theorem, our path integral f dot dr.